So, today is our first lecture on machine learning, last main topic of this course. So, let's see what this is all about. Until now, we've looked at how to make optimal decisions. That has often involved probabilities, but we've assumed that these probabilities are given to us. Somebody provides them and we just use them. In machine learning, what we're going to do is we're going to look at data that isn't given to us in that nice format, just raw data, and we're going to somehow build models from the data. This could be learn the parameters in a BaseNet. This could potentially be learning the structure, that is the graph that constitutes the graphical part of the BaseNet. And it could be learning hidden concepts, let's say structure and data. Let's say you look at Google News. What you see there is the result of a clustering. You see per topic of that particular day, you see a bunch of articles clustered together that are on that particular topic. Today what we're going to do is the first thing, which is we're going to learn parameters for a naive Bayes model, which is a special type of BaseNet that's really useful for classification. So what's classification? Pretty much this is what it is. You have some input, you look at it, and then you bin it in some output category. The running example for us is spam versus ham. So you get an email, and spam is the bad email, ham is the good email. So setup is you get something like this into your computer. Dear sir, first I must solicit your confidence in this transaction. This is by virtue of its nature as being utterly confidential and top secret, and so forth. And the computer's task is to decide whether this is spam or ham. Probably spam for this one. So computer would say spam. Next one, to be removed from future mailings and so forth. Again, probably computer should categorize that as spam. And then the last one, okay, I know this is blatantly over time, but I'm beginning to go insane. Had an old Dell Dimension XPS sitting in the corner and decided to put it to use. I know it was working pre being stuck in the corner, but when I plugged it in, hit the power, nothing happened. Well, probably ham. It seems like they're not trying to sell you anything. Maybe somebody you know emailing you. So that's what we want as our final system, something that can recognize whether an email is spam or ham. This can be very personal. This can depend not just on the words that appear. It can depend on how the words are typeset, capitalized or not capitalized. It can depend on whether there are a lot of typos or not. It could depend on who the email is coming from. So for any given email, you have a list of things that you think could affect the outcome of it being spam or ham. And you somehow, we're going to use that as our input, that abstraction of that email, and then classify it as spam or ham in an automated way. The largest setup is that in machine learning, to build this system, the first thing we're going to do is collect a lot of emails, and somebody is going to tag them as spam or ham. So that's the first phase of the process. Once that has been done, somehow we hope that these examples are enough for the computer to then learn what the right classifications of future emails that come in. In current systems, who's doing the labeling? He raises his hand. He's doing the labeling. Anybody else? Actually, everybody's doing the labeling. Whenever you get an email that's undesirable, you label it as spam in the hope that it never makes your inbox anymore, something similar in the future. You might sometimes be lazy and not label it as spam, so there's a little bit of noise in the labeling. So it's a noisy process, but in principle, you're getting labels that carry some information. Whenever you click on spam for an email, Google knows, let's say, that was a spam email. When you don't, they figure it's not. Okay, once you have a big enough data set, enough examples, presumably the computer can figure it out on its own, and we're going to look at how that might happen. Our other motivating example is in computer vision and digit recognition. So what are we looking at here? Let's say that's a 0, right? Over here, harder to say, maybe a 7, maybe a 1. Over here, probably a 2. Over here, probably a 1. Down here, not really sure. So the task here is you get some kind of digit written down. This could be an application. Your application could be reading checks. automatically, or you could be reading addresses on mail envelopes automatically, and you somehow have to figure out what the numbers are that are appearing on this particular scan that you made. So the input will just be pixel grids or images. What that means is that you have somehow a value here, maybe between 0 and 256, that you get for each pixel, and somehow that sequence of numbers you want to map to one of these 10 possible digits. That's the goal. The setup will be similar. The first thing you do is you get a very large collection of images that all contain digits, handwritten digits, and you label them. Often, if you don't have immediately anybody to label them for you, if you can set up a game where people like to play some kind of game, and part of the game is labeling it, that's one thing people do. Another thing people do is they post them on Amazon Mechanical Turk and pay, let's say, 1 cent per label. And that way they get their labels. The goal is that we then learn from this data how to predict on our own. That is, the computer just gets a new scan and knows what digit it is. Again, whenever we get this raw data, we translate it into features. So rather than working with just a vector of pixel values, what you'd probably rather do is use a representation that's a little more meaningful for this task. In this case, you could have something that says, well, what's the number of loops you see in this particular scan? What's the aspect ratio for the number? What's the number of connected components that you see? Those are features that could be more informative than just looking at the raw pixel values. And a lot of the work in building good classifiers actually goes into building good feature extractors. So what we'll cover today is a way to build a classifier, assuming somebody gives you the features. And once you know how to build a classifier, you can program that once, keep it fixed for every future classification problem. But whenever you have a new problem, this part will actually end up have to redo and be clever about what you choose there to feed into your classifier. What are some other classification tasks? One thing to think of is, if you're going to look back at this AI class, the most likely thing that you're going to use from the entire class is classification. Of all things we cover, unless you go into the gaming industry, that's probably the technology that's used the most nowadays. Here are some examples. Spam, we already covered. OCR. Then another one, medical diagnosis. The input there is symptoms that are maybe measured on a patient. And the classes, so the output of the classifier are diseases. Another application that ETS uses is automatic essay grading. The input is a document, so some typed text, and the output is a grade. Fraud detection. The input is the activity on your credit card account, and the output is whether a transaction that just happened is fraud or no fraud. When you send an email, that email might automatically get routed somewhere based on what's in that email and get classified into different types of people that might help you out, and so forth. So there's a lot of applications out there underneath a lot of automated services that really use classification at the core. There's also kind of a slight variation on classification where you don't per se bin things, but you might rank them. So you want to have a sorted ordering of things from most relevant to least relevant. We'll later see that techniques used for that are very similar to techniques used for classification. And then you have a whole other range of applications, such as presenting with maybe advertisements to you in order of relevance to you, maybe search results in order of relevance, maybe items in a Facebook newsfeed are presented to you in order of relevance, and so forth. So there's a lot that's happening with classification these days. This one here, that's actually, well, pretty much the state of the art in computer vision. If you can recognize that with your classifier, you build a really good computer vision system. So visual tasks are still really hard. So spam versus ham. First thing we're going to look at is model-based classification, and what that means is that we'll build a model for what each class looks like, and then when we get something that comes in, we'll just compare it to each of these models and see which models would predict best what we just saw. So in this case, our model will be a BaseNet, and we will model in the BaseNet both the label and the features. So we don't put the original input in the basenet, but the features instead. Then when we get a new example coming in, we instantiate any of the observed features, and then all we have to do is run inference in the basenet to find the most likely label given the features we observe. Okay, so once we have the basenet, we're essentially done. We just have to run probabilistic inference. The question is, what structure should the basenet have, and how do we find the parameters for the basenet? Here's one example. Let's say you build one for digits, and in a very naive model, you could have something where you say, well, once I fix the label 0, 1 through 9, that's the class, then all the other things that I'm going to look at, namely all the pixel values, f1 is the 0, 0 coordinate, f2 is the maybe 0, 1 coordinate, and so forth. They're all going to be independent of each other once I know the label. So it kind of assumes that when somebody writes a digit, they choose which digit they're going to write, and then individually fill in each pixel, not worrying about what they filled in other pixels, just thinking about the label. Oh, it's a 9, so pixel 1, yes or no, you have some probability, and then you fill it in or not. It's a very strong assumption. It's probably not the way people write digits, because usually your pen stroke is continuous. But it's just an assumption that we're going to use, and in fact, assumptions like this will often violate reality, but still you'll get something reasonable out. Question? So y is what's in their head, and we have no idea. At test, when we get a new scan, we don't know what they were trying to write. All what we'll get to see is the pixel values themselves, and we'll hope to run inference in this basenet to back out what they were most likely thinking in terms of digit that we're trying to write. So if you use this model, here's your joint probability. Let's see, y, given all the features, is what you want to find once you see all the feature values for a new scan. You can compute this as proportional to the join between y and all the features individually given y. For this to be Bayes rule, you would also have to divide by the probability of all the features. But since the probability of all the features is not dependent on y directly, and all we care about is finding the y that's most likely, we can ignore this, because it will not affect who is the winner among all y's, and we can just look at this part, and based on that score, which y is the most likely label. Okay, so we know if somebody gave us a basenet in this particular format, and we get a new image, we can fill in the pixel values, we can run inference, we can find the most likely digit that was written. What we need to learn is still the parameters in the model. So for naive Bayes model, this is our structure. All we have to specify is how each feature depends on the class. So we have some dependence f1 to y, f2 to y, and so forth. So these are very small conditional probability tables. You just have one parent variable, which is great. It means a relatively small number of parameters to be learned. But we still have to find them somehow. So how many parameters do we have? In this case, we have number of parameters n, which is the number of features. F, which is the domain size for each feature. And y, size of y, which is the domain, the number of digits in case of the digit example. In general, number of class labels. This here is the size of one table, and then we have n of those because we have n features. So our model here will scale linearly with the number of features, which is a great property in that you can throw in many, many features and you'll still be able to work with them. So very simplistic. We'll actually see more complicated models next lecture, but this one still will often win out even though it's such a simple model. So how do we run inference in this naive Bayes model? Very straightforward. Once we have the labels, all we need to do is compute the joint of, once we have the features, all we have to do is compute the joint between the features and each label. So we have to do this as many times as there are variables y. We have the joint. It's going to give us a table, one for each possible label. The way we compute it is just a product of the prior with the probability of each of the features given that particular label. Each of these can be computed independently. If you had a parallel system, you could do this independently for each of the labels and come back with numbers for each one of them. And all you need to do is see which one gets the highest score. Whichever one gets the highest score in this table is the one that you output as your classification label. And you can even get an estimate of the probability of that being the right label by renormalizing by the sum of all of them. So the procedure is fairly straightforward, very fast also. If you get a new, let's say, email in or scan in, the computation is very quick. You just run through each conditional probability table, pick out the corresponding entry, and then multiply them together, do that for each label, and compare. Okay, we've seen how to do inference. It's similar to what we've seen before. How do you get the conditional probability tables? Well, the first one we need to find is Py. The other ones we need to find is a conditional for Fi given y. Combined, we call those the parameters of our model. For now, in all past lectures, we have just taken those as parameters that are given. What we're going to change now is that we're going to take data, from the data, figure out what theta is, or more concretely, figure out what the entries should be in Py, and the entries should be in the conditionals for the features given the label. So let's take a look at what type of conditional probabilities we'd like to have. Let's say you have a digit classification task. Maybe, your prior could be something where everything is equally likely. And then for each feature, you have something that says how likely it is for that feature to be on given the class label. So for this particular grid square over here, it's almost never on when the digit is 1. It's almost always on when the digit is 0. Almost always on when the digit is 5, and so forth. So that's what this table is telling us. And we need to build a table like that for each of the grid squares in this image. For text, what would these tables look like? Often we make additional assumptions. So the model we use is that Wi is the word at position I. Again, we build a model of this type here. Probability for the word, a particular word, given the label. Now, usually what is done in text, which is called a bag of words model, is that you assume each word in this naive Bayes model is independent of what type of email it is, giving each word is independent of each other, giving what type of email it is. So you're saying once I decide spam or ham, word 1 and word 2 are chosen independently. It's a very strong assumption. In fact, in speech recognition, we saw that most likely that's not the case. We built hidden Markov models that model how the next word depends on the previous word. But in this naive Bayes model, we assume that every word is picked independently. What that means is that effectively you're not having a good model for language, but if somehow the task that you're trying to solve really depends on which words occur, this might still work quite well. This is done to make the model very simple. So this is the simplest model you could build while still getting fairly reasonable results. And so it's efficient to learn the model, efficient to do classification with the model, but you lose some information, but it might not have been relevant information to recover the label. So the word could be, you build a dictionary, and the possible values for a word at a given position could be any entry in your dictionary. If you have 100,000 words in your dictionary, that's a lot of different possible values it could take on. Compare this with these pixel values here, where we said it could be black or white, or maybe it could be something between 0 and 256. For words, you'd have a lot more options. So often a simplifying assumption that is made to not have to learn a separate huge conditional probability table for each position in the email, let's say, is to learn the same conditional probability table no matter where you are in the email. So the conditional distribution for word 1 is the same as the conditional distribution for word 2, same as for word 3, and so forth. So it assumes that essentially the word ordering doesn't play a role in how people choose what words they put in the email. It's another assumption, but it's something that allows you to have only one conditional probability table for word given type of email, as opposed to one for each position in the email. If you make that assumption, it's like not looking at your email in sequence, but just grabbing all the words, throwing them in a bag, and considering that as what you're looking at. And so because of that, it's called a bag of words model. Again, the motivation is not that we think people independently pick words in that way, in the same way in every position, but it's just that having a different model for each position in the email would just require a lot of models. They're all very large, and so to reduce the amount of complexity, just use one model instead of as many as you have words in your email. Okay, so let's look at an example. We have the spam filtering example here. We have, let's say, there's just one word model. Then we have a distribution for the prior, spam or ham. We have a distribution for when somebody produces a word, what it would be as a function of already knowing it's spam and when you know it's ham. Let's see what it looks like. Here's what the distribution could look like for ham versus spam. Maybe 33% of the emails you get are spam. Would be a reasonable model to just look at those counts, put it in there. Then here's another model. You could look at the counts of how often in a spam email the word the occurs, the word to occurs, and so forth. And then look at the empirical frequency and call that the probability of occurrence of that particular word. You could tabulate that. And same for ham. And this table would maybe go 100,000 deep, right, if you had 100,000 possible words. Let's assume we have this model, and we'll see a couple of ways of getting this model more formally later. And we now get a new email coming in. Well, the prior says 33% spam, 66% ham. So what we often do to make this computationally practical is we'll work with, instead of the product of the probabilities, we'll take the logs. So this thing here is the log of 0.33333. This one here is the log of 0.6666, and so forth. And now we'll keep track of the score as we go along. So this is our classifier in action. What we're doing here is we're computing Py times Pw1 given y, Pw2 given y, and so forth, as we go along for the two different values of y, spam and ham. And we keep a running score as we go along. And rather than computing it this way, we'll keep track of the log of this rather than the original number. The reason you do that is because if you multiply a lot of really small numbers together, at some point your computer will think it's 0, everything will look 0, and you won't be able to distinguish the numbers anymore. By keeping track of the logs, you get a meaningful range of numbers that you're looking at. So this thing starts with Gary, that apparently has probability of 0.0002 when something is spam, but a much higher probability when something is ham, maybe because you are Gary, and so a lot of emails have that word in it. Question here? We take now the product of these two numbers and take the log, gives us this number over here. And same thing, this number over here is the log of 0.66 times 0.0021. And in practice, the way we keep track of this is by, we already had the log of 0.666, and then plus the log of 0.00021. And keep this running sum as we go along. Next word, would. Okay, again, we take the log of these two numbers, and then add them on and keep track of the running sum here. For now, ham is looking better with minus 16 than spam, which is minus 19, which is a worse score. This one favors spam. Like to lose weight while you sleep. We keep track of the score as we go along, and we see minus 76 for spam, minus 80.5 for ham. So in this case, spam is the winner because it has the best score, according to our classifier. Yes? Yes, you do. Oh, great question. So what if there's a word that you don't have a probability for? We'll see how to fix that. Right now what would happen? It would go wrong, for sure. Yes? Is this sort of the reason that a lot of spam has misspelled words in it, trying to throw off thinking extra time? I think the reason a lot of spam has misspelled words in it is because people misspell, and they try to make it look as much as real people writing email. But what they do, I mean, aside from misspelling, that's very related, is they throw in random words, right? A lot of spam will have maybe text from real emails thrown in somewhere, maybe at the bottom, especially for this bag of words model, the bottom or the top wouldn't matter. So just throwing at the bottom a lot of stuff that comes from real emails. And now this type of classifier would now realize that things at the bottom are less relevant than things at the top, and you could fool it. I mean, what you're really getting at there to some extent is that really there's a game here, right? It's more complicated than machine learning, actually. We're looking at it from a machine learning point of view. We're getting that data. We learn to classify spam versus ham. But once we're done, if the spammer knows what algorithm we use, they could go in and tweak their spam to defeat our algorithm and, again, have it be classified wrongly by us, right? Absolutely. If you want to go back to probabilities, just to make it very explicit, what this is here, this is the log probability of the label n, so the label in this case, spam, and f1 through f2 for, well, let's call it n. If you want to go back to actual probabilities, all you have to do is exponentiate these two things. And then you have the probabilities back. These are the joint of the label and the features. Then you renormalize, and you get back out the conditional probability of spam versus ham. So in this case, for example, the conditional of spam given f1 through the last feature is equal to e to the minus 76 divided by e to the minus 76 plus e to the minus 80.5. That will give you the probability of spam, which in this case probably would be really close to 1.
You calculate probabilities of war rate like 1. How do you get probability?
Where did these come from?
Yeah. So
the simplest way to get these is just frequencies. You would look at your data. You'd say, how often did I see the word the in a spam email, let's say? And I just say, well, the is maybe 0.01% of the words is the, and then that would be the number sitting there. So what this number means here, this number here would mean that if you look at your corpus of ham emails, 0.01 if you randomly picked a word in a ham email with probability 0.01339, you would get the word 2. That's what that number means. Same for this one over here, let's say. This one says that if randomly from your corpus of spam emails, you pick the word out of an email, then with probability 0.01517, you would have found the word 2.
So as you analyze spam, your probabilities change, right?
The bigger a corpus you have, the more accurately you'll be able to estimate those numbers. And they'll ideally converge to something when you have a really, really large corpus. Any other questions about this? Yes?
In the bank of words model, does it matter whether you put the same word as there? Like if the spam word is there, that's more classified as spam than this one.
Okay, so let's look at that. Let's say a word appeared again, right? Let's say look at a word that's very spammy, maybe wait. Yeah, that's pretty spammy here. Wait. If that appeared again, let's say that word appeared again at the end here, then we'd again have a 0.00016 here. We'd again have a 0.00002 here. And if we took the logs of that number, that would be the difference between those two numbers, right? For the first one is something like minus 8.8. So you do another minus 8.8. This would become minus 84.4. And then this one here was minus 11, so this would have become minus 91.5. So your score would have favored spam even more than before. So you're really looking at every entry in the email, and each of them contributes independently. There are actually other models. You can build other models that maybe are not as popular, but in principle you could build a model where you have a feature for each word in your dictionary, and the feature then says, how often is this word present in this email? That'd be a different type of model, but you could build a model just as well that way. Yes? Absolutely, yeah. And there are things where, I mean, a lot of other things are being looked at. This is just the words, right? Typically, spam filters will look at the sender. They might have access to how many emails that sender has sent with the same text in it. They might have access to maybe having other people already labeled something as spam. So if you got an email, you label it as spam. Maybe another person got the same email in their Gmail account, and Google might realize, okay, that's another feature that we need to use, how often other people have labeled it as spam. So they try to, you can use anything you might have access to, and a lot of the work goes into thinking about whatever would be most informative. So what you would have then, let's say, somebody else had, there was an additional feature, you would keep track of however many other people have maybe extracted something as spam already. You have an additional feature here, number of times flagged as spam by other people, right? And maybe for that feature, the value would be, if let's say it were 5, so to say, then you would have a probability here for the probability of being flagged 5 times as spam, given that your spam maybe is, or bigger than or equal to 5, maybe is the feature, then maybe the probability is 0.95. And probability of being flagged as spam when it's ham is maybe only 0.001. And something like this would then contribute a lot to the score and heavily favor the prediction to be spam. Okay, let's take a break here. And after the break, let's look at the entire pipeline, train, practice, and final. Yes? How many times do you need to go through this loop? Yeah, we'll get to that. We'll get to that very soon. So here's a cartoon for the remainder of lecture, and which is maybe the most important thing about machine learning is this cartoon here, is that when you do machine learning, there are three parts to the process. The first part is when you train. That's, you're in lecture, you're at home, doing your homework. That's the training part. That, in machine learning, will take most of your data, just like for you, it'll take most of your time, presumably. Then, you wonder whether you did the right training. You do a practice exam. If you don't do well on the practice exam, you go back and you retrain. Maybe you'll have a better result and go back to the practice exam. Keep going back and forth. That practice exam in machine learning is called validation. So this thing here, we'll call training. This is validation. And then once you've done enough training and validation so that the validation tells you that you're in good shape, you go on to the real test, and presumably you do equally well. That's the idea. You do equally well on the real test here as you did on the validation. But you never get to see the real test until you actually go into the real test, and that real test will tell you how good you are, or in case of a machine learning system, this will be your Naïve based classifier, which will here be classifying actual things that need to be classified, and you'll see, well, how well does it perform. But in more machine learning terms, when you get your data, you actually split it into three sets, shown here. Maybe this is about 70%. Maybe this is 15% and 15%. The training data is what you use to do the bulk of your work. And so that could be, for example, you look at the frequencies in your training data, and based on that, set the parameters in your BaseNet. The held out data is where you then use your Naïve Bayes model on some data and see how well it works. If it doesn't do well, then probably you go back and you say, well, this wasn't doing well. What can I do different at training time? Well, what's available to you? One thing you can do is you can choose different features. So you can decide to think about new features that you throw into the mix, or maybe take features out. Maybe you had too many features, you take some out. Then you can go back, learn with those new features, see what the parameters are in your Naïve Bayes model, do the holdout test, see what your score is, and keep working in this loop until you think you got a good set of features. There are also some other hyperparameters that we can choose. For example, you could not just choose features, but you could choose the algorithm from today's lecture versus the algorithm from next lecture, and compare them both on the holdout data, see which one does better, right? And finally, when you made your decision, you think you're done training and validating, that's when you go to your test data and you report how well your classifier does. That's your final number, that's how well your system does. So this is a cycle in which you actually tend to go around a lot. Other things you could do is you could say, well, my algorithm is not the right algorithm, it's not just the features. You could tweak the algorithm. Again, after tweaking the algorithm, you look at your holdout accuracy, and if it's better, well, maybe your tweak was in the right direction and you keep tweaking, right? So this is really what you use the bulk of your time. And at the very end, when, let's say, you deploy your system, you're about to deploy your system, you can run on the test data, and the number you get on there will be presumably predictive of what you'll get in the future on data you've never seen. Because you've never peeked at the test data, you haven't been able to tailor your system to the test data. It's data you've never used before, so you can imagine that it has predictive value for other data you've never used before. If you're a researcher, what you do is you work with this, and then this is separate here, the test data. Once you're done working, you invented your new algorithm or your new set of features. You go to the test data, you see what the number is, you put that number in your paper, and you say, my system got this accuracy on this task. Okay, so accuracy would be the fraction of things you classify correctly. That would be one reasonable measure. The main thing we need to worry about here, and why we have this split, is that we need to worry about something called overfitting, avoiding overfitting, and ensuring we have generalization. And we'll see more of that later, but the idea here is that you don't want to build a classifier that just works really well on the training data and then doesn't do well on the test data, right? I can give you a classifier that does really well on the training data. Just memorize every training example, and then when somebody presents you one of these training examples again, just look it up, you say, oh, that was the label, you get it right. But then when you get test examples, they won't be matches. You won't get identically the same thing, and then you don't know what to do at all. So that's a very poor representation to use if you want to do anything reasonable on the test set. Yes? Okay, so actually, let's go a little further and see an algorithm of how we might specifically go through this loop, and then I'll clarify where exactly the training data is used, where the held out data is used. But for now, you can imagine that you have two different sets of features that you're thinking could be good, and for both of those sets of features, you build a naive Bayes model based on the training data, and then for both of those learned models from the training data, you validate on the held out data, see what the score is, and whichever one does best is the one you then stick with, and you would go on moving that one to the test data. At a high level, what happens is in the training data, you use for kind of the bulk of your parameters. You learn with the training data. And then usually there are some tweaking parameters that you have left. And those tweaking parameters are the ones that you kind of loop over all settings of the tweaking parameters and see which setting of the tweaking parameters results in the best held out data performance. And then that's what you use as your result. So let's make this a little more concrete. What we're worried about is underfitting versus correct generalization versus overfitting. Overfitting is when you are really good on the training data, but bad on the test data. Underfitting is when you don't even do well on the training data. You just have a model that has maybe only one feature or two features, and you stand no chance even on the training data to do anything good. And then, well, you're not going to do well on the test data either. Overfitting we've seen before. Remember this plot here? We said, oh, let's do reinforcement learning with a feature-based representation. We need to learn the weights of the Q function in this feature-based representation. And let's think about in general. Let's say we try to learn the coefficients of a polynomial that goes through these points or approximately through these points, but that at the same time has good values not on those points. I said, well, you have to be careful if you have a polynomial of a very high degree, let's say a 15-degree polynomial, you could get something like this. It's doing really well on the training data. The error on the training data is 0 everywhere here, almost 0 here. So really good training data performance. We don't see the test data here, so we don't know how well it does on the test data, but you could imagine that the real pattern would not predict this value here or this value here, and that this is not a good way of fitting this data. And what happened is you gave the algorithm a lot of coefficients in the polynomial so it could fit the data really well, but as a consequence, it did it in a weird way, and that's not what we want. Okay, here's another example of overfitting in the context of what we've been looking at. Let's say you do digit classification, and we're going to classify this one here and check whether it's a 2 or a 3. All right, let's run our naive Bayes classifier. Let's assume we learned the model, right? We have some numbers. And we say, well, the prior says equally likely a 2 or a 3. And let's look at the first feature. It's a very naive feature, but let's just go with it. Whether this pixel value is on or off. Probability for on, assuming it's 2, is 0.8. That's a high score. Assuming it's 3, it's also 0.8. So far, we still have a tie. Then for the next pixel that we're looking at as one of our features, probability of being on for a 2 is 0.1. For a 3 is 0.9. So right now, the 3 is ahead. Continue. Here, for being off, we have 0.1 for a 2 and 0.7 for a 3. So this far, if we were to stop here, the 3 would win over the 2. Now we continue. We'll look at another feature down here. It's kind of a weird feature in that corner. It says for a 2, it's 0.01. probability of being on, and for a 3, it has a 0 probability of being on. Now, we multiply them all together. Here we have 0. Here we have some number that's bigger than 0, so the 2 wins. So what just happened here? By having this 0 in the model for 3, it overruled everything else. How could we get that 0? Well, imagine you have a training data set in which you have scans of 3s, right? This type. And let's say you never had this one filled in. You had 100 examples, and all 100 of them, it was not filled in. You use your empirical frequencies to set your parameters. You get a 0 out of 100. That's your 0 right there. And then you're stuck with a 0. And whenever that pixel is filled in, no matter what other evidence is coming in, you'll always say this is not a 3. For the 2, it happened to be the case that 1 out of the 100 examples had that pixel filled in, and that now helped it win. This is an example of overfitting, where you looked at the training data, you saw it was never filled in for a 3, and you say, oh, I got it, I really know what it means to be a 3. You really can't have this filled in. You're overfitting the training data, and now here's the result. So you want something that doesn't do this kind of stuff. Here's another example. Let's say you look at email, and what we're going to look at here is actual numbers. So Dan Klein collected a bunch of email. He works in natural language. He does a lot of language stuff. Collected a bunch of email, and he actually built a Naïve Bayes model on the email he collected. Maybe one of his students, who knows. So we're going to look at this quantity over here. What is this quantity? Let's say you build this classifier, you build your Naïve Bayes model, and you wonder, well, what did I really learn? Well, the way the system works is that when a word comes in, it contributes to the score of ham and it contributes to the score of spam. And the relative way it contributes is how it affects the outcome. It's not the absolute probability that matters, but it's the ratio between probability of the word given ham, probability of the word given spam. If this ratio for a word W is really high, that means it heavily favors ham. If you see that word somewhere, you're going to push really hard for ham. Other way around here, if you see a word with a very high ratio of the right-hand side type, that'll really much push it towards spam. So we can, after we have learned the classifier, we can go in and we can analyze the data and we see, what did we really learn? What words are indicated of spam versus ham? Let's start looking at these. Well, this is what you get. Southwest, infinity. Nation, infinity. Morally, infinity. Nicely, infinity. Extent, infinity. Seriously, infinity. So what's going on here? It means that this quantity here was equal to 0 for these words, meaning that none of the spam emails had this word in it. You just took the empirical frequencies, so they got that 0, very similar to the 3 having the 0 down there. You get that ratio of infinity. Once you see one of those words, you're going to always call for ham. How about spam? Same thing there. The top ones are all having a ratio of infinity. What does that mean? It means that none of the ham emails had the word screens in it. That's all this means. We somehow don't want this. This is overfitting. You shouldn't say, because in my training set, the word screens was never in a ham email. That means if it appears, it's guaranteed to be spam. Okay, so this is what we just discussed, is that you have to be careful with these zeros that end up showing up if you just look at empirical counts. We want to do something better. We don't want the zeros to show up. That's the main issue that we've had so far. So we somehow want to smooth the outcome of our estimator. We don't want to just use counts. We know that's not going to do the right thing. So we want something that moves us away from the 0. So let's look at parameter estimation. We've been talking about just using counts from the training data to set the parameters. Let's look at what that means in terms of what we are doing. You're trying to estimate the distribution of a random variable. You don't know what the probabilities are. So what happens, you could ask somebody to tell you. That can be hard. Maybe they're not there to tell you. It could just be too many probabilities to think of, or it could just be a probability that's just hard for a human to come up with. What's the probability of a certain word in a ham email? A person will have a very hard time telling you a good number for that. So what people typically do is you train it. That's what we've been looking at. That's machine learning. You could look at the empirical rate. So if you had a bunch of red and blue jelly beans in a little bowl, and you wonder what's the fraction of red in this bowl, you could pull out 3 at random. You could see how many of them are red, and you could say, well, I think 2 out of 3 in this bowl are red. We're just pulling out 3. That's a very small number of examples to generalize from, but maybe if you pulled out more, you get a reasonable estimate of the actual fraction in here that is red. So what we do there is we just look at the count and divide by the total number of samples. In this case, 2/3. There's another way to get this result. So this result is very intuitive. You could say, well, just look at the counts, that's it. But there could be other probability distributions where looking at the counts might not be the right thing to do. And so we're going to look at what are we really doing here in a more general way is doing something called maximum likelihood. That's what the ML stands for. What that means, we look at the likelihood of the data. So L here is a new quantity, is the likelihood of the data. L, X, theta. X is the data, and theta is the parameter. And so if you have a bunch of data points, then it's the product of each of the probabilities of each of the data points. Let's do this for this example here. So what's the probability if we had a distribution, which in this case, color could be red or blue. Our parameter is theta for red, which means 1 minus theta for blue. What is the likelihood of this data set over here? Well, the first one is red, has a probability of theta. Second one is red, has a probability of theta. Multiply it together. The last one is blue, probability of 1 minus theta. So the likelihood of that particular data set with a parameter theta is equal to this. What we can do now is we can say, well, if you want to know what the best choice of theta is, we can say, let's just find the theta that maximizes this score. If we find the theta, which is called the theta ML for maximum likelihood, which is the argmax over all theta of theta times 1 minus theta. By choosing that particular choice of theta, we maximize the probability of seeing the data we just ended up seeing. So it's a very reasonable thing to do and a very general principle. For any probability distribution that has some parameters, if you see some data, you can multiply together the probability of each of the data points and then find the parameters that maximize that product of probabilities. In this case here, we have, let's do some math, we have theta squared minus theta to the third. To find the maximum, let's take the derivative. dd theta is equal to 2 theta minus 3 theta squared. Set that equal to 0. One solution is theta equals 0. Another solution is, let's see, 2 minus 3 theta equals 0, which means theta equals 2/3. So we have 2 solutions to setting the derivative equal to 0. The theta equals 0 here, that's not a good one. That score would be 0, so that's probably a minimum or some other kind of weird point. The 2/3 gives us a maximum. To verify that, we actually have to take the second derivative. So we take the second derivative, dd theta squared, gives us 2 minus 6 theta, which at theta equals 2/3 gives us 2 minus 6 times 2/3, which is equal to minus 2, which is negative, which means we have a maximum at theta equals 2/3. So this might look like a very roundabout way of finding theta equals 2/3, but the nice thing about this approach is that it's very general. You can apply this to any distribution that has some free parameters that you don't know. You can always multiply the probability of data points together, find the maximum among all the choices of parameters, and use that as your estimate. Any questions about this? Okay, so that's maximum likelihood. we haven't yet seen how we're going to smooth this. Yes? Oh, we can do this for all our entries in our conditional probability table. So you could imagine having a Bayes-net, right, as we've been looking at, and you'd have a table. You'd have a table of the type y, py. Maybe it could be spam or ham. You call this one theta, this one 1 minus theta. You look at all your data. You look how many emails are spam, how many ham. You multiply it all together, find the maximum likelihood estimate. You fill it in, and you found this conditional probability table here for y. Same thing could be happening for features. Let's say you had feature 1, y, probability of feature 1 given y. You would have maybe plus f1, plus y, minus f1, minus y, plus f1. Actually, let's put plus y first, minus y, minus f1, minus y. Now you'd have a theta for the case of plus y, a 1 minus theta for the case of plus y. Then we have a theta for minus y, and a 1 minus theta for minus y. So we have two free parameters in this conditional probability table. And when we get data now, we could say, well, maybe we can even label this one explicitly as theta y. We had a data point come in. Let's say first data point was plus f1 plus y. Next one was plus f1 minus y. Then the likelihood of this data under this model, we would have likelihood equal to, look at the first one, we have plus y, so that would be theta y, if this was the plus y entry. Theta y times the probability of f1, we assume the model looks like this, y f1, times the probability of f1 being plus f1 given plus fy, which is this one over here. So theta plus y. That's the first one. Multiply with the probability of the second one, which is theta 1 minus theta y times, we have plus f1 given minus y, which is this one here, which would be theta minus y. So now we have a new quantity here, the likelihood of this particular data set under this model. And we can now, for this, find the max over all choices of theta y, theta plus y, and theta negative y, which are three parameters. So it's a three-dimensional optimization problem. We find a choice of parameters that maximizes this quantity, and those are our maximum likelihood estimates. And those are the numbers that we use to put into these tables over here. Yes? Compared to? Okay, so how much slower is this compared to doing the frequency stuff? Well, if you do it this way, and you compute the derivatives, you'll see that the result is always equal to just using the frequencies. So for this type of table, where you just have categorical data, you can just look at the frequencies, you get the same as the maximum likelihood estimate. And so, but now if you, let's say, had a different distribution where somebody said, well, your distribution has to be of the type maybe a continuous distribution. The function of x would be maybe e to the minus lambda x or something like that. And you get some data points for x, maybe 1, 1.5, 5, and 7. Then you can do the same thing there. You can multiply together the probabilities of each of these data points and find the parameter lambda that maximizes the likelihood of the data. So the key here is that this is a very general principle, and often you'd ahead of time, in closed form, find the form of the solution. So you wouldn't actually run a hill climbing search to find the solution. You would ahead of time set the gradient equal to 0 using a parametric equation, all in symbols, and then you would know what the result is. So for our case, this 2/3 was a result either way. Okay, so that's maximum likelihood. Likelihood is the same as just looking at the counts. So we still have the problem that if the count is 0 for something, that will overfit and land with a 0 in a conditional probability table that will overrule everything else. So we have maximum likelihood. That's what we just looked at. It happens to come out as the count over the total number of samples. Instead, you could think of these samples as evidence, as observations of your parameters, some noisy observations of your parameters. Right? So you could say, let's instead then find the most likely a posteriori value for theta. So map maximum a posteriori. That means that you find the theta value that is most likely conditioned on the data. How do we find that? Well, let's apply Bayes' rule. Bayes' rule says that this is equal to the conditional of the data x given the parameter theta times the prior and then divided by the probability of the data. We just want to find the theta value that maximizes this. So this part doesn't have theta in it, so it doesn't matter. And we can just find the value of theta that maximizes this quantity over here. What do we have now? We have the same thing as before, sitting right here. X given theta, that's the maximum likelihood. So if our p theta, our prior for theta, would be, in some sense, would be equal for every choice of theta, then we'd still get the same as the original. Then it wouldn't affect the result. On the other hand, what we can do here, we can favor certain values of theta a priori. And we could say, I'm going to put maybe even a 0 or a very low weight on the possibility of having a theta that allows parameters to be 0. Yes? Yes. So what we're doing here is we're reasoning about a distribution over our parameter theta. So we're saying theta is something we don't know. It's a random variable. We get some evidence from the training data, and we're going to back out a distribution over this unknown variable theta. And then from that distribution, we're going to pick the point theta where the distribution is the highest. What do we get here if we do the math? It depends on your choice of p theta. But key is that if you choose a p theta in a clever way, you can avoid these 0 estimates. So let's look at this in a little more detail. What we really want to do is avoid these zeros. And the way this originally came about was a philosopher / mathematician, Laplace, and he was worried about what the probability was that the sun wouldn't rise the next day. Okay? And he was keeping track how every day, marking off whether the sun had risen or not. And if you use maximum likelihood estimates, then obviously if you wanted to assign a probability to the sun rising, which is one number theta, you'd put it at 1, because every time it's risen in the past, so 1 would be the number. But it seems if you want to reason about the future and want to account for the, you say, well, I'm not 100% sure the sun would necessarily rise every day. You can't use the maximum likelihood estimate. So you have to do something a little different. So what did he do? He said, instead of keeping track of my counts, when I start counting, I add in a fake count. So before I start keeping track, I add in one occurrence of the sun having risen, one occurrence of the sun not having risen. And from then on, I keep track of the counts. So if there's 2 fake data points, and by assigning these 2 fake data points, all 2 possible outcomes have been seen from the beginning, and so you'll never end up with a 0 in your probability tables. So mathematically, what you get here, if you did maximum likelihood, let's say x is red, you get 2/3. If you did Laplace smoothing for x equal red, you get, well, the count for red is now +1 fake red, and you have +1 fake blue. So you'd end up with 3/5. Another way to get the same result is, and if you want to take something like 281a, you'll see that, is to add a prior p theta, which is equal to theta times 1 minus theta. So if down here, we chose our prior p theta to be exactly of this format over here, we would then get the same as Laplace smoothing. So both are equivalent. So we have two ways of getting here. One is putting in a prior. Another thing is to just say, hey, I just think we need to put in a fake count. It's the same thing. Why a count of 1? It's pretty arbitrary. There's no reason to pick 1. All right? Question here? Yes. What you do is, as a prior, you generate a uniform probability over all possible outcomes. In this case, the 2 possible outcomes. But you can generate that prior in different ways. So if you look at the equation, you use the count, the actual count, plus the fake count, divided by the total number of things you actually saw, plus the fake count that you have for each possible outcome, times the number of different outcomes possible, right? So what you have here is 2 possible outcomes, so size x would be 2, and k is a parameter that we get to choose. So what we're saying here is, the previous slide here at k equal 1, add a fake count of 1 for everything. There's no reason to pick 1. You could pick 0. If you pick 0, you're back to maximum likelihood. You're back to equal red 2/3. If you pick 1, that's what we had on the previous slide. So we had a red that was fake and a blue that was fake. We had 3/5. If we pick 100, well, then we'd have this 100 times. We'd have this one 100 times. We'd end up with 102 red over a 203 total. You can also pick a k that is not an integer. You can pick 0.01, you can pick 0.5, whatever you want to pick. You can go through this procedure. It'll work. You get an estimate of your parameter theta. As long as you pick it different from 0, you'll have introduced a fake count strictly larger than 0. You will not have the zeros in your conditional probability tables. You won't have the issues we had at the very beginning when looking at spam and digit classification. In practice, the way you pick k is how certain you are about something. Let's say you had a coin flip, and somebody gave you a coin. You wanted to estimate the probability of the coin being heads versus tails. You'd say, well, that's a coin. I know coins. Maybe I put in 1,000 and 1,000. And then you start collecting data. You'd work from that. If somebody gave you a thumbtack, well, maybe you're not that familiar with what happens when you toss a thumbtack in the air and see how it lands, pointing up or down. Maybe you say, well, not that familiar, but I do think both outcomes are possible, and both have some reasonable probability, so maybe I'll have 5 and 5 as my fake counts that I introduce. So this is prior knowledge that you introduce, that you get to tweak. This is something more advanced that you can look at yourself. We're not going to test you on it. Let's look at the numbers that you get out when you use Laplace smoothing. Now, what's the most indicative of ham versus spam? The font Helvetica being used, the word seems, group, ago. We don't get these original things with scores of infinity anymore. We get much more reasonable things. Here for spam, font Verdana apparently in this data set was the font that spammers were using at the time. Credit is a word that occurs a lot in spam emails, but not in ham emails and so forth. So this is a lot more reasonable. This actually makes sense. So our choice of k probably was a good choice here. All right, so how do we choose this value of k? This is really where it all comes back together, is we said there are 3 types of data sets, or 3 parts of your data set: train, hold out, and test. Your choice of k, you have many, many choices for k. You will learn your naive Bayes model for many different choices of k. As a function of k, the lower k, the better you will do on the training data. Why is that? This is good. Well, k smooths things out, takes you away from just fitting the training data as accurately as possible. So the higher k, the less well you fit the training data. On the holdout data, what you get to see is, well, maybe with a low k I'm overfitting, I have these zeros and so forth. And the kind of pattern you'll see is that on the holdout data, with low value of k will not be the best. If k goes up, you'll start doing better. because you'll generalize better to this holdout data by putting in your fake counts. But if k is too high, so this point here is overfitting. You fit the training data too much. If your k is too high, you get underfitting. Everything just stays uniform. You're not even looking at your training data really. Very high values of k. And somewhere in between will be the sweet spot. Now, to avoid that you choose that sweet spot, but the reason we have a held out set is because to choose that sweet spot, you want to look at your held out set. It allows you to choose the sweet spot, and most likely that sweet spot will be roughly the same for your held out data and for your test data. And so in your test data, you'll do well if you do well in your holdout data. When can you count on this kind of pattern where if you do well in the holdout data, you'll do well in the test data? That'll work as long as you have only a small number of parameters that you're looking at. Here we have one parameter. That's fine. As long as you keep it relatively small, maybe a handful of parameters, this will work out well. All right, that's it for today. Next time.